In this video, we're going to talk about span and linear independence. We will start with the definition of a linear combination of vectors. So a linear combination of these vectors are going to be scalars times each of the vectors added together. So again, if you have m vectors, each of the m vectors may be multiplied by a scalar, and then you add it all together. That's a linear combination. So our first examples are going to start with the vectors 2, 1, negative 3, and 1, negative 2, 4, which you might also see written in this form. I think your book uses this form, but I noticed in class your teacher's using this, so every now and then I'm going to throw this in. So because if you multiply the 2, 1, negative 3 by 6, and if you multiply the 1, negative 2, 4 by 5, the resulting vector is going to be 17, negative 4, and 2. Therefore, we say that the 17, negative 4, 2 is a linear combination of 2, 1, negative 3, and 1, negative 2, 4, because there are these scalars, 6 and 5, that can multiply your two vectors, and then you add it all together. That will give you the 17, negative 4, 2. Kind of to compare, the vector 17, negative 4, 5 is not a linear combination of 2, 1, negative 3, and 1, negative 2, 4. And that is because there are no scalars, alpha 1 and alpha 2, such that if you multiply by your two vectors, you'll be able to produce the vector 17, negative 4, 5. So again, it's because A1 and A2 do not exist. So we say it is not a linear combination. And I'm going to use this example to say that there are two ways you should look at these equations. Whenever you have these vector equations, there are two different views you should have of this that you should always have in mind or be able to go back and forth between. And the first view is you should think of these two vectors as kind of building blocks that you can use to make this vector here. So how do you use these two vectors? So this is where it's useful to think of this in terms of the pictorial on a Cartesian coordinate system. That you have this vector here, you're going to stretch it by 6. So you're going to make it 6 times as long. And then here you're going to stretch this vector 5 times as long. Then you're going to add them together in order to make this vector here. So I think of these two vectors as sort of building blocks that can allow you to make this vector. So again, that's one kind of concept you want to have. That is the concept that vectors can be stretched and then combined together to make other vectors. It's almost like when you have Tinker toys, like you combine them together to make something new. So again, you're stretching and then adding or combining them to make a new vector. So oftentimes you're asking yourself, how do I stretch and then combine which vectors in order to make the vector that I'm interested in? So I have these scalars here just as variables. And so what this also looks like, so the second way of picturing this, other than stretching and then adding or combining your vectors, is you think of this as an equation. So when I look at that equation, I can multiply in my scalars, and then because I'm adding two vectors, I can add them together this way, and they're still equal to this vector on the right-hand side. And then essentially, because vectors are like coordinate by coordinate, so the 2a1 plus a2 has to equal 17, and the a1 minus 2a2 has to equal negative 4, and then minus 3 and minus 3a1 plus 4a2 has to equal 2. Essentially, you are given this vector equation gives you three linear equations. So essentially, this vector equation here, or this vector equation here, they're equivalent, gives you a system of linear equations. And you learn how to solve these in middle school at some point. So The two views that you want to keep in mind when you see these vector equations is they can represent stretching or contracting different vectors and then combining them, adding them together to make a third vector. And you can also think of this equation as representing a system of linear equations. So back to our original problem where we're trying to get 17, negative 4, 2, this system does have a solution where a1 is equal to 6 and a2 is equal to 5, and you can put that into the system of linear equations and it will work. However, if you look at the equation where you're trying to get 17, negative 4, 5, where there is no solution a1, a2, right? What we would say is that system of linear equation has no solution. So when you can't, when your two vectors cannot have a linear combination to make a third, then the corresponding system of linear equations has no solution. So the next thing we have is the definition of span. The set of all linear combinations of a list of vectors v1 through vm in the vector space V is called the span of v1, v2 of the vectors. It's the span of the vectors. It's denoted span and then list of the vectors. So the span of the vectors said a different way. It's all these linear combinations, so the a sub i's are all scalars. So it's all possible. You multiply the scalars times the vectors and add them together. And last, the span of the empty list is defined to be the 0. So from our previous example, we saw that 17, negative 4, 2 is in the span of 6, 1, negative 3, and 1, negative 2, 4, because there is a linear combination of these two vectors that make this vector here. And I have it notated here that 17, negative 4, 2 is an element of, that's supposed to be my epsilon. It's an element of the span, or it is in the span of 2, 1, negative 3, 1, negative 2, 4. Then we also had the 7, negative 4, 5, where there was no solution. So we would say the 17, negative 4, 5 is not an element of the span. In terms of what I told you about these vectors being stretched or contracted and then combined together to make this other vector here, 17, negative 4, 2, to be in the span means that this set of vectors can be used to construct this vector. It is in its capability, it's in its span, I guess, its reach will reach this vector. You can make these vectors. If it's in the span, you can make the vector. Whereas this vector here is not in the span, it is unreachable by this set of vectors. It cannot be made by these vectors. So now we have this following theorem. Span is the smallest containing subspace. The span of a list of vectors in V is the smallest subspace of V containing all the vectors in the list. So I'm going to skip the proof that it is the smallest subspace, but I am going to go ahead and prove that it is a space. And if you recall, there are three things I need to do to prove it is a subspace. First, I need to show that the additive identity is in the space. Then I need to show it's closed under vector addition, and then show that it's closed under scalar multiplication. So I'm going to start with additive identity, but that's easy. All I have to do, of course, that's always bad when your teacher says all you have to do, because usually it's really long. But this is truly an all you have to do, is set all the a sub i's equal to 0, and then you have the additive identity of 0. So next I have that it's closed under vector addition. So if I have my first vector, I'll just say that it is of this form, a1 v1 plus a2 v2 plus am vm. And then I'll have my second vector, I'll just call it b1 v1. So it's a different vector in the span, so it's different coefficients in front of the same vector. Some of them could be 0. When I add them together, I'm going to get a1 plus b1, a new coefficient in front of my first vector, a new coefficient in front of my second vector, and I keep doing that, and I keep getting new coefficients by adding the two coefficients together. to my last vector, but so I have new coefficients, but it's still in the span of my vector space because it's basically just stretching them now by this new coefficient. And the last thing I need to show is it's closed under vector addition. So again, I have my representative vector over here. It's a linear combination of my vectors, and then I multiply it by a scalar, but by definition, you just multiply it, each term by a scalar. That's gamma AM, VM. So again, all I did is I have new coefficients now, but they're still real number coefficients multiplied by my scalar, so I'm still in the span. So because I've shown all of these three things are true, I have shown that the span of a list of vectors is a vector space. So again, just to say this another way, because you really do want to remember this, if you have a list of vectors and you consider all possible linear combinations, then that space, all those linear combinations, is going to make a vector space. And again, the span of a set of vectors is in fact a vector space. So another definition, so if we look at the span of a set of vectors, that's a vector space. If that vector space is called V, we say that the vector spans V. So an example, show that 1, 0, 0, 0, 0, 1, 0, 0, well basically this set of vectors spans Fn, that is the set of all n tuples. So I have rewritten these vectors kind of in this vector form, like this. And essentially, you should recognize this. You can do this not just for a four-dimensional vector, but in R3, R2, R6, whatever. Basically, the 1 is in the ith element. So for the first vector, the 1 is in the first position, and the other coordinates are 0. For the second vector, the 1 is in the second position, all the other coordinates are 0. So for the ith vector in this list, the 1 is in the ith position and zeros are in all the other coordinates. So again, the fourth vector, the 1 is in the fourth vector, zeros in all the other coordinates. And this this kind of pattern for vectors is the canonical set of vectors for Rn. And the reason why it's canonical is because basically to show that you can get any vector, let's say you're in 4 space, so in F4, it's very easy to show that these 4 vectors span the space because you can make any vector in F4 from these 4 just by simply putting in the coordinates as the coefficients. And so again, if you're in R2 and you want a set of vectors that spans R2, what you would do is you would list these 2 vectors because any vector in R2 can be composed from these 2 vectors. So we have the definition of a finite dimensional vector space. So a vector space is called a finite dimensional. Vector space is some list of vectors in it spans the space. So for our previous example, we saw that these 4 vectors spans F4, which means F4 is a finite dimensional space. And in fact, it's a 4-dimensional space. So our next definition is of a polynomial, which you totally know, but here it is in your book. A polynomial is a function p that maps from f to f. Again, f is the complex numbers and real numbers. Is called a polynomial with coefficients in f if there exist scalar coefficients a through m such that p of z, and here the z is, instead of p of x, the z is there to emphasize that it could be a complex number, is equal to a0 plus a1x plus a2x squared all the way to amxm. And then this capital P of capital F is a set of all polynomials with coefficients in f. And here we have the theorem that PF, again the set of all polynomials with coefficients in F, is a vector space, and it is a subspace of F to the F. And actually, we proved something very similar when we were talking about vector spaces and subspaces. So for the proof, I'll let you go back and look at the last video. So I'm going to assume you know what the degree of a polynomial is. That is, if it's a third degree polynomial, that means its largest exponent is 3. I do have this definition here. It's kind of convenient, although really you don't need it really. But anyway, your book uses it, so we're going to go over it. This capital P with the lower script m with capital F denotes the set of all polynomials with coefficients in F and degree at most m. So this is a set of polynomials whose degree is at most m. So here we have an example problem in your book where it says that P3 of F is a vector space. In other words, all polynomials of degree at most 3. And that is something that we proved in our last video, so I'll let you see that video there. Another definition. We had the definition of a finite dimension vector space. So a vector space is called infinite dimensional if it is not finite dimensional. So an example of infinite dimensional is to show that the set of polynomials is infinitely dimensional. So the solution is to consider Pm of F, which is finite dimensional. It has a dimension of m. So once you have a set of vectors, right, that covers your m degree polynomial, you can always find another polynomial that is m plus 1. And it's not going to be in the span, hence no list spans P of F, and thus P of F is an infinite dimensional vector space. And finally, we're on the definition of linearly independent. So a list of vectors in V is called linearly independent if the only solution to this homogeneous equation, a1v1 plus a2v2 up to 0, is all of the coefficients is equal to 0. So some intuition behind the linearly independent. It means, again, the only linear combination of these vectors that will give you 0 is if all of the vector coefficients is 0. So in other words, there's nothing that looks like a1v1 plus a2v2 that will give you 0. If there were something like this, where a1v1 plus a2v2, if there did exist a1 and a2 that were not 0, what that would mean is you could write v2 in terms of a1, in which case you would kind of think of as v2 as being dependent. So another example, if there were coefficients a1, a2, a3 that were not 0, such that you can add up the three vectors with their linear combination equal to 0, if these were not all equal to 0, that would mean that v3, that would mean v3 is a linear combination of v1 and v2, meaning v3 could be made from v1 and v2. So it's not independent. It's something that you can actually make from v1, v2. So it's kind of dependent on v1 and v2. So independent means you can't make any of these vectors from some other little subset of these vectors. It means they all kind of stand alone by themselves. When they're dependent, that means at least one of the vectors can be written as a linear combination of the other vectors. In other words, at least one of the vectors can be constructed by stretching and lengthening other vectors and adding them together. So you want to note that v1, v2 up to vm is linearly independent if and only if each vector in the span has only one representation as a linear combination of the vectors. So to look at this, let's assume there are two representations for v, and we have this set of coefficients, our a set of coefficients, as well as our c coefficient. So if we subtract v from v, we get 0, and we have the a1 minus c1 v1, a2 minus c2 v2, etc. But because the vectors are linearly independent, that means this homogeneous equation, homogeneous meaning it equals 0, means that each of the coefficients, a1 minus c1, has to equal 0, which implies that a1 equals c1, so there's actually only one representation. So again, if they're linearly independent, then each vector only has one representation. It's unique as a linear combination of the vectors. So some examples of linearly independent sets. A list of one vector, a list V of one vector is linearly independent. So one vector by itself is linearly independent. A list of two vectors is linearly independent if and only if neither is a scalar multiple of the other. So you can't make one from the other unless it's a scalar multiple. These canonical bases, so when you have when you're at R4, if you have the ones in the 1 position, 2 position, 3 position, 4 position, if you're in R through 3, it's sort of the same sort of idea. These vectors are all linearly independent because you can't stretch this vector to make any of the others because you would also have to rotate, and all you get is stretching and adding. The list 1 z squared up to zm is linearly independent, not literally, but linearly independent in the polynomial. So this is kind of your basis for your polynomial. And then a good definition for being linearly dependent. Well, a list of vectors is linearly dependent if it's not linearly independent. Our first example of linearly dependent, these three vectors are linearly dependent because 2 times the first vector plus 3 times the second vector plus -1 times the third vector is equal to 0, 0, 0. And again, another way of looking at this is they're linearly dependent because one of these vectors, let's just say, actually you could have chosen any one, but I chose 2, 3, 1 is equal to the 7, 3, 8 minus 3, 1, 1, 2. And then again, if I really wanted to construct 2, 3, 1, I would divide everything by half. So essentially, they are dependent because one of the vectors can be composed from the other two. There are things about them that are in common. So another example using those same 3 vectors, except with the c here. So these 3 vectors is linearly dependent if and only if c is equal to 8. And in our last example, c was equal to 8. So this proof has 2 parts because of the if and only if. So first we're going to do the forward direction and show that these 3 vectors are linearly independent. That is that C1 plus C2 plus C3 equals 0, 0, 0. Means C1, C2, and C3 must be equal to 0, will imply that C is equal to 8. The second part of the proof is to show that if C equals 8, then the vectors are dependent. But actually, we just showed that in the last example, the previous example. So we only have one part to do. So the first part of the proof is to show that these 3 vectors are linearly independent, meaning C1, C2, C3 must be equal to 0, must imply that C equals 8. So when I looked at this, remember, we can also view this as a system of linear equations. So here are there linear equations I have. I have my 2c1 plus c2 plus 7c3 equals 0. I have my 3c1 minus c2 plus 3c3 equals 0, and my c1 plus 2c2 plus c3 equals 0. So one of my least favorite things to do is solve systems of equations, but here we go. So first we're going to combine these 2 equations because I can get rid of my C2. So first, so I combine these two equations, I add them together, I got a 5C1, these cancel out, I get a 10C3, so I get that C1 is equal to minus 2C3. And because I have this C3, and I'm trying to solve for C, I'm going to try to solve for C2 in terms of C3. So what I'm going to do is I'm going to plug this C3 into C1, so I have only terms of C2 and C3. So again, I'm going to plug my C1 equals minus 2C3 into this equation here, and I'm going to get minus 4C3 plus 2C2 plus 7C3 equals 0, and that's going to give me C2 is equal to minus 3C3. So I will plug that all into my last equation. So I've plugged in my C1 here. So I have my minus 2C3. I plug in for C2 here. So I have minus 6C3 plus C times C3 equals 0. And then as when you work this out, you'll see that C must equal to 8. Yay, I'm done. So another example, if some vectors in a list of vectors is a linear combination of the others, then the list is linearly dependent. And I'm going to let you try to prove that. But again, what you're going to use is the fact that one of the vectors can be written in terms of the others. So then you can have the one vector minus the way you write it in terms of other vectors, and you can equal it to 0. Another example, every list of vectors containing the 0 vector is linearly dependent, and the reason why is once you write your linear combination of all your vectors, and your 0 vector is one of the vectors, then this coefficient here can be any number, it doesn't have to be 0. Next we have this lemma. Suppose you have a list of vectors and it's a linearly dependent list in V. It's linearly dependent. In other words, one of the vectors can be written in terms of the others. Then there exists a jth vector such that the jth vector is in the span of the other j minus 1 vectors. Again, because it's linearly dependent, that means one can be written in terms of the other. So that means that one vector is in the span of the remaining j minus 1 vectors. And if the jth term is removed from the m vectors, the span of the remaining list still equals the span of the m vectors. Again, because the jth term was kind of redundant because it really could be made up from the other vectors, that means the remaining vectors still span the same space. So make sure you understand this because this should be something that it's kind of obvious once you understand all the terms of linearly dependent and span. This should make total sense to you. So here's another theorem that should totally make sense to you, but it's a little bit hard to explain and maybe takes a little more thought, a little more time to think about. But again, once you see it, you should actually be able to read it, think about it, and then it should make sense to you, but I'm still going to explain it to you anyway, because that's the whole purpose of the video. But again, you want to get to where, if you think about it, you really can understand what's going on. But here you have a finite dimensional vector space. In that vector space, you have a set of linearly independent vectors. And then it talks about the length of every spanning list of vectors, but we're first just going to consider one spanning list of vectors. So we have a list of linearly independent vectors, and we have a list of spanning vectors. So here I have my spanning vectors. I have W, my set of W. I have n of them. The span equals V. They span the vector space. And then here I have my set V of vectors that are linearly independent, and I have j of them. So what this theorem is saying, that to span the space, you have to have at least j vectors, because this is a set of linearly independent vectors, and there are j of them. So minimally, there needs to be j here. And the reason for that is that these j linearly independent vectors means you have at least j vectors that really cannot be made from the other vectors. They are totally dependent. They can't be made from one another. So there's j of them. And so that means in here, there's no way you're going to get less than j vectors that will be able to make all of these vectors. So if like W1, if you could make V1 from W1, maybe W1 is 1/2 V1. So then to make V1 from W1, you just multiply by 2. So maybe you could make V1 from W1, but once you can make V1 from W1, that tells you that you can't make any of these others, V2 through Vj from W1. Similarly for V2, you have to have some vector that does not allow you to make V1, has to be in W that makes V2. And then on and on. So your V sub j vector has to have some vectors in W that makes it that hasn't been able to make the other vectors because these vectors are independent. So hopefully that makes sense to you. I think there might be a formal proof in your book. Actually, there is a formal proof in your book, but you can take a look at it. I actually didn't think it made as much intuitive sense to me, so I gave you this other awkward, long-worded explanation instead. But if that didn't work for you, take a look at your book. Plus, we do have a couple of examples that are coming up on the next slide, so maybe that'll also clear things up or make it more clear to you. So here's an example. Show the list 1, 2, 3, 4, 5, 8, 9, 6, 7, and -3, 2, 8 is not linearly independent in R3. So remember when I told you that there are these canonical bases or vectors? So this set here spans R3 again because you can make any vector in R3 from these three bases just by taking the coordinates and writing it as the coefficient, right? So here we have a set of vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1 that span R3. But by our theorem, it talks about the length of every linearly independent list of vectors. It has to be less than or equal to the length of every spanning list of vectors. So here we have 3 vectors that span. So any list of linearly independent vectors needs to be less than or equal to 3 according to this theorem, which means these 4 vectors cannot be linearly independent. So again, here we have our list of 4 vectors that we're trying to determine if it's linearly independent. But our theorem talks about the linearly independent list of vectors. But the theorem says if it is linearly independent, the list of vectors will not exceed the number of vectors in the spanning list, right? So the list of linearly independent vectors is going to be less than or equal to, it won't exceed the length of the list of spanning vectors. So here we've used this theorem to show that this is not linearly independent. And technically, I guess if this were homework, I would say not, but I'm out of space, linearly independent. And I can't spell it right either. Okay. You should make that conclusion on your homework, and you should do it better than I did. So here we have another example, and I think this is our last example for this video. Show the list 1, 2, 3, -5, 4, 5, 8, 3, and 9, 6, 7, -1 does not span R4. So we have 3 vectors, and we're hoping to span R4. And just to remind you, we have our canonical bases, and I know we haven't talked about bases, but just in case, I don't know, you're reviewing, but we have our canonical bases, our 4 vectors that span R4. Since there's 4 of them, you kind of expect you need at least 4. But we're going to use these 4 in our theorem. So these 4 vectors are definitely linearly independent. You can't make one from the other. So this is a set of linearly independent vectors, and there are 4 of them. So we have our 4 linearly independent vectors, and then we have these 3 vectors that are hoping to span the space. But according to our theorem, the list of spanning vectors has to be greater than or equal to the number of linearly independent vectors, and this is not the case. There's only 3, but there's 4 linearly independent vectors. So for that reason, these set of 3 cannot span the space. So here I have my conclusion by the theorem. You need at least 4 vectors to span the space. So I'm going to say does not span. And you should write a better conclusion on your paper. Last theorem and last slide for this lecture. Unfortunately, I didn't cover all of chapter 2 in this lecture. We still have to talk about bases, but I'm going to do that in a different video. But the last theorem, every subspace of a finite dimensional vector space is also finite dimensional. And hopefully that doesn't surprise you. Okay, well, I guess we'll finish chapter 2 in another video. Thank you for watching.